Okay, any questions? So I want to finish. We want to finish up adding different groups to the benzene ring, and then we'll talk about some more modern methods here today and Friday. So the problems that were in the Monday's folder are due Friday. The problems that are in today's folder are due next Monday, and then the top hat problems for Chapter 21 are due next Wednesday. And there's going to be some problems in Chapter 21 that you're not going to have to do, but I haven't taken those off the list or send you an email and said don't do these problems. But they'll be the ones in the sections that aren't on the reading list. Okay, so where are we at here? We are at. We'll come back to blocking strategies. We kind of ended up here with the entry into how to add more groups. So I mean, we know a pretty decent amount of reactions. I mean, you're probably saying, yeah, we know a lot, or we need to know a lot by next week. But we can't, there's certain things we can't make on the chart. I can't make a C triple bond N. I can't add an N group like NH2. I don't know how to add an OH group. So we need to talk about those reactions that we can use to make at least all the groups that are on the chart. So the first step in doing that is to realize that if we have a nitro group, if we place a nitro group on the ring, we can reduce that nitro group using either iron or tin, HCl, and heat. And if you do that reaction, you're going to end up reducing the NO2 group down to an NH2 group. So this is a reduction. Also, I believe in the top hat text they say that you can use H2 and palladium on carbon to do this reaction. That would just be a straight hydrogenation reaction. Either one, I think the iron, HCl, and heat is a little bit easier to use than trying to deal with hydrogen gas or palladium metal. Whenever you see palladium on palladium parentheses carbon, what that means is palladium's really expensive, and so is platinum. So instead of just dumping chunks of metal in, which would be super expensive, when all I want is the surface of those pieces of metal to react, what they do is they basically absorb the palladium or platinum onto the surface of a charcoal bead or carbon bead. So it's a lot cheaper method, and all I'm interested in is the surface anyway. So most of the mass of the bead is carbon, but the surface where I really am interested, that's palladium. And so that's what PD parentheses C means. It's palladium on a carbon surface. So this is a straight reduction we're adding hydrogens and making an NH2, making an aniline. So this is how we can make group number one. And from this, we can make a number of other groups. So we already talked last time about how to make benzoic acids. We could do it by Grignard. We could do it by alkylation and then oxidation with KMNO4. And then we'll come back to this idea of blocking. So once you're able to add an NH2 group to the benzene ring, that you can make what's called a diazonium salt. So if you react any amine, that's NH2 is the amine, if you react an amine with HCl and sodium nitrite, and this is NO2, not NO3, so this is nitrite. If you react HCl, sodium nitrite, you make what's called a diazonium salt. And it turns out that if it's just a normal alkyl group that's attached to the diazonium salt, you have to be careful because they're not stable, because I've just put a nitrogen gas molecule into that, attached it to that alkyl group, and if you're not careful, that's going to explode. But if you put the diazonium and put it in conjugation with a benzene ring, it's nice and stable. And so that makes an aryl diazonium salt. And those are stable. We don't have to worry about them exploding or anything like that. And they give us the ability to add or substitute then a number of different groups for this N triple bond N. Okay. And so what kinds of things can we do with that? Well, first we just have to remember it's 2 steps to the diazonium salt. It's always 2 steps. It's actually 3 steps, because you've got to put an NO2 group on the ring. You got to put an NO2, then convert it to an NH2, then convert it to the diazonium. So it's an automatic 3 steps to get you to diazonium salt anytime you want to react it. First thing we can do is do what are called Sandmeyer reactions. So in the Sandmeyer reaction, what I'm going to do is take the diazonium salt and react it with a copper salt, a copper 1 salt. So either copper chloride, copper bromide, or copper cyanide. And if you do that, what you end up doing is substituting the diazonium salt for that group. We already know how to put a chlorine and a bromine on the ring, but this allows us to put a C triple bond N on the ring. So if you wanted to make a nitrile, if you want to add a nitrile group to the benzene ring, it's basically going to be like 4 or 5 steps. You got to put the nitro, convert it to NH2, convert it to diazonium, react it with copper cyanide. And that puts that would put a C triple bond N group on the ring. So there's one more group that we couldn't make previously on the chart. So now we know how to make that one. And so Sandmeyer reactions are useful. Like I said, we know how to put chlorine and bromine on the ring. There may be times when people want to put a chlorine or bromine on the ring through the Sandmeyer as opposed to just directly with Br2 and AlBr3 or Br2 and FeBr3. Then there's more. Now, I used to have this chart where the diazonium salt was in the middle and all the arrows were going off in a wheel. And actually, you'll probably see those kinds of things on the exam, on old exams. Because it really starts with the same thing. So take your diazonium salt, react it with acid. That's how we make phenols. Because that is a phenol. So that'll allow us to make group number 2. Put the OH on the ring. Then there's some other groups that we haven't quite talked about. If you use HBF4, that will put a fluorine on the ring. We haven't talked about how to put a fluorine on the ring, but this is one method to do that. Well, other than the HBF4, which is kind of a weird acid, it works well. And you might say, well, do we really need a fluorine on the ring? There are many pharmaceuticals that have fluorines attached to their benzene rings. And so that's done quite often. If you want to put an iodine on the ring, you could use the diazonium with Ki or sodium iodide. And that'll put an iodine on the ring. Notice I'm not talking about the mechanisms of any of these, nor will I. And then if you want to take the diazonium salt completely off and replace it with a hydrogen, you can use H3PO2, which is again it's kind of a strange acid, but that will put a hydrogen on there. I'm not quite sure why you would want to do that. other than to maybe remove a nitro group or maybe remove an aniline group from the ring. But you can do it if you'd like. So the diazonium salt is pretty useful. Now the problem is the diazonium salts are covered in like chapter 23. So if you want to, so in the reading assignment, it'll show you where these are at. So you're not going to find any problems in chapter 21 on diazonium salts because all the chapters, because they're all in chapter 23. So when we get to chapter 23, you'll do those problems. But the diazonium lets us puts an OH group on the ring or an NH group on the ring, which are important. Okay. So that's, you have to, there's another 5 or 6 3x5 cards. That's more like 10, right, when it's all said and done. But one of the things you'll see is, so you'll see that I gave you problems for Friday and for Monday, some of which are to do these sequence of reactions. And some of them, step 1, you add a bromine, and step 2, you add a magnesium, and step 3, you do this. So those are the kinds of problems you'll see next week. Hopefully then, if you have begun to learn the reactions, then you can just kind of go through them and test yourself. The other kinds, there are other problems in the electrophilic aromatic substitution folder that's underneath, I think, today's. There are tons of problems, some of them not very easy. I kind of, when I sit down and decide to write, I just write it out and then I try and figure out the answer later. And so some of those are like 10 steps. You would never see anything like that on an exam, but they're good, challenging problems that'll make you learn all the reactions or use all the reactions in the entire set. And that's if I give you a benzene ring and say, how do you make this out of the benzene ring? And you'll have a couple of those on next week's exam. Just 2 or 3. Usually it's like choose 2 out of 3. So, but you will have to do that. So we'll talk a little bit more about that probably Friday or Monday, after you've gotten a chance to do some of the forward problems. Now, what's next? So, and the last thing you can do is something that turns out to be a pretty big, well, historically turns out to be kind of important, and also then the production of what are called diazo dyes. So when you have a diazonium salt, there's 2 resonance structures for it. There is the one that we've been writing or that's been on the slides, and then if you move a pair of electrons over, you can put the plus charge at the end nitrogen. What happens there is that if I look at this resonance structure as the reactive form of the diazonium salt, I can look at this as nothing more than a big E+. And so if I react my diazonium salt with an activated ring, and this has to be an activating group, which means that it's going to direct this electrophile to both the ortho and the para positions. But because of sterics, it's probably going to go more para than ortho. Jacob? It cannot be a halogen. So it has to be, this has to be a true activating group. And usually what's done is it's nitrogen or oxygen. But if you react this diazonium salt then with an activating group, it's going to direct it mostly para because of sterics. And you're going to end up then with this N plus being, this whole thing then being the E plus and adding to the activated ring. Now the diazonium salt itself can have different groups attached to it, but the actual nucleophilic ring has to be an activated ring. And so what you end up doing is making what's called a diazo dye. Now in lab we skip talking about ultraviolet and visible spectroscopy. And it wouldn't have been a very long lecture anyway. Why do organic materials have a color to them? Why are some colorless? Why are some orange, red, etc.? Because that molecule absorbs one wavelength of light and it transmits another. And you can, there's a color wheel that has the complementary colors on at 180 degrees, so that if something absorbs blue, it transmits yellow, I think is the way the color wheel works. There might be a color wheel on one of these slides. So, and then you can do that, like if you're looking for the perfect power tie shirt combination, you're supposed to take your tie and make sure it's a complementary color to your shirt. I have one of those. Obviously, I don't use it very much, but it's supposed to be the most, I don't know, there's different tie theories. I'm sure there's other clothing theories out there, but that's the complementary one. So what happens is that if we want to make a material that has a color to it, it needs to absorb visible light, because that's all we can see. How do you get a molecule to absorb visible light? Give it lots of conjugation. So when we make diazo dyes with benzene rings in conjugation with N2 groups, with conjugation with other rings, we might have an SO3H group, which is more conjugation. We can actually tune these diazo dyes to different colors and make them as they were different colors. And I mean, making color materials is a huge business, right? I mean, we didn't splurge on color paint for the walls. But if we do, how many companies are out there that are making, paints? A ton. Probably less than what you'd think, because some of them are making the paints for like Home Depot. It's probably a Sherwin-Williams or PPG or something like that. Car paints are huge. And then you can get the car paints where the color changes depending on how you're looking at the car. You walk around it, it has like 5 colors. That's called chroma key. You could end up with that's a huge industry as well. So just putting color, it's like Sherwin-Williams is like paint the world. That's their company motto. It's important, and that's something we spend a lot of money on. We spend a lot of research money on. How do you do that? You make conjugated materials if you want dyes. Now, dyes are soluble. Pigments are not soluble. So we're talking dyes here. So if you want to dye a piece of cloth, you just need to get something that absorbs visible light. I think one of the more famous examples was that back in the 16, 17, 1800s, purple was the royal color because that dye only came by going to some isolated island in the Mediterranean, digging up some little insects and crushing them, and they gave the purple color. And only the rich people, only the kings and queens could afford that. But then there was a chemist in England. He was like 16 or something. He's like some little smart aleck kid. And he had like a chemistry lab in his basement. And he was trying to make quinine, which would have been a cure for malaria. So not only he's a philanthropic kid too. But what he ended up making was a really dark solution that when he kept diluting it, it ended up being this royal purple color. And he did it using coal tar that I think I talked about before. That's kind of the mother's milk of aromatic compounds. And so he made this purple dye, and now all of a sudden, apparently they had Fashion Week in Paris still back in those days, because that was all the color, that was all the rage. And so he made this purple dye, and so then everybody could have purple clothing. Because he showed that basically you could synthesize the dye. Before, people were trying to synthesize just cures from coal tar, but now you can make these other products. That opened up the chemical industry in England, and and Germany. And then ultimately that got transferred over to the US. So he made a diazo dye that was purple, not quinine, which somebody else then was able to make. You've used these diazo dyes. If you've done general chemistry lab, you've used these. If you've used some of the dyes, I know Faith has a whole sheet in her lab notebook on all these different dyes and what their pH and what their color transitions are. Methyl red is one of those dyes. And so at one pH, methyl red is yellow. At another pH, it's red or orange. So when you're doing your titration, you can see the change in color and know where your endpoint is. That's an example of a diazo dye. And also it shows that if I put like a carboxylic acid here, or I put an aniline instead of just an NH2, I could make a dimethyl aniline. I can change the color of the dye. So here's just an example of all the different colors you can get, from deep red to yellow red to deep yellow to orange, just by changing the groups that are attached to the ring. When you add a nitro group, remember a nitro group is an N double bond O with an O minus, that adds conjugation onto the ring. And what happens is that the more conjugation you have in an organic molecule, it changes the wavelength at which it absorbs from ultraviolet into the visible region, and then the more conjugation makes it absorb at a higher wavelength. So you can change the wavelength of absorption, which means you change the wavelength of transmission by changing the structure. And this is just with organic dyes. This isn't with any kind of metal compound that you might see like in a painting, where they're using pigments of different metals. This is all just totally organic dyes. So you'll find these, you can find these, I think, in acid-base indicators. You could certainly, if you've ever taken cabbage and made like the cabbage juice indicator, pH indicator, that is using molecules that are similar. So that's just kind of a practical use of diazo dyes, but they're incredibly important just from the whole idea of making dyes and pigments of different colors. There's tons of people employed around the world whose job it is just to look at that. And occasionally we've offered a class called the Chemistry of Color, which really should be the physics of color, because it's much more complicated than just chemistry. And the person who teaches at Dr. Singham, she ran the color lab down at Sherwin-Williams before she retired. So she knows way too much about making different color pigments and dyes and the physics behind it. But I don't know when that's going to be offered in the future, but she's retired. And the students, I said to the students, I said, you realize who you have teaching that class? Because there's only like 4 color labs around the world. So that anytime somebody comes up with a new color for a car or a house paint, there's only like 4 labs that are coming up with that. Even a different shade is sometimes difficult. So anyway, that's how we do that, and that's what we would talk about if we did UV vis spectroscopy. Okay. So those are all the diazo dyes, and also the diazonium salt reactions. Right, so that kind of, until you do some practice problems, you won't have a real good sense, but that's how we can make those different molecules. So not only do you have to know them in terms of what product they produce, but you'll need to remember the reagents in case you want to add that group to the ring. But it's just a long series of reactions. Nitro, NH2, diazonium, whatever else you want to add to the diazonium. So those series of reactions you're going to want to bundle together in your head. Now let me just go back and let's talk about blocking. So we've talked a little bit about protection in terms of when we use the silyl chloride to protect an alcohol from being reacted. Blocking is kind of like that, but it's kind of totally different. So one thing we need is, if you're going to do any kind of anything that's reversible, it has to be reversible. And so the one group that we can put on the ring and take back off again is a SO3H group. So we can put an SO3H group on the ring with sulfur trioxide and H2SO4, and we can take it off with steam. So if we take our molecule and we pass steam over it, or we heat it with steam, we can actually get the SO3H group to come back off of the ring. So that's a reversible reaction. And how would you do that? How would you do this kind of a reaction? Where would it be useful? Well, let's say that I gave you this problem. Or let's make it a real problem. So I'm working at a company, or I just am doing academic research, and I need to make this molecule, and I want to make it in the highest yield possible. So I want to make the orthobromotoluene, and I want to make it basically 100%.
So why don't you add the SO3H group in the para position? Because there's only one para position, and that'll only add ortho.
Right, so that's what we're going to end up doing.
And then you can remove it with steam.
Right, so we're going to use this blocking strategy to make this compound in the highest yield. Now you might say, okay, I'll just put the methyl group on the ring. I'll put the methyl group on the ring, and then I'll add Br2 and FeBr3 to it. And if I do it that way, what I'm going to end up doing is I'm going to end up forming two products where the bromine would add ortho and para. And you might say, well, what add the bromine first? Same problem. If I add the bromine first and then I add the methyl group, it's going to go ortho and para there too. And there I'm going to pay a higher energy cost, because when I put a bromine on a benzene ring, that's a deactivated ring, so it's going to take more energy to make the methyl group add. If I start with the methyl group, I'm going to take less energy to add the bromine because the methyl group's activated. Right? We have to take all this stuff into account if we're going to do this reaction on a large scale. So if I have like a round bottom as big as this room, and that's the kind of scale I'm doing the reaction on, and that doesn't really, I've only ever heard of a round bottom room size from one person who went and interviewed at a company. When I was in graduate school, they came back and said, this company had a round bottom as big as a room. And I'm like, okay, that's pretty impressive. Because most things are done in steel tanks. So if I'm working and I'm trying to make a ton of this material, the problem here is I'm going to make a half a ton of that material. I'm going to make a half a ton of waste, which probably means that my company isn't going to last very long, because we've just made a half a ton of waste, and unless I have somebody to sell it to. So when we do reactions in the lab, if we get a 25% yield, it's no problem. We just dump the stuff into the waste container. When you're trying to make a ton of material, there is no waste container big enough. So you have to kind of think of, I want to optimize my yield. And then you get into chemical engineering where that's all you do. But in this case, this is not a good approach. It's not a good approach to just make both products and throw one away. So what can I do? Well, my approach would be, let's put an SO3, H2SO4, let's put the sulfonyl, or let's put the sulfonyl group on the ring. And because the SO3H group is large, it's going to go to the para position almost 99+%. Adding the SO3H group to the ortho to the methyl group is going to be pretty small percent. So I'm going to put the SO3H group para. And now if I do my Br2 FeBr3 reaction, the methyl group is the more activated group. It's higher on the chart, right? Everybody hopefully knows that now, although you'd say, but SO3H isn't on the chart. No, it's not on the chart you memorized. But S double bond O immediately makes it an X double bond Y group, which makes it deactivated. So activating versus deactivating, activating directs. And so that methyl group is going to direct. Now the para position is blocked so that the bromine will now go to the ortho position exclusively. And you might say, well, there's some steric issues there. Yeah, but the bromine's got to go somewhere. So it's just going to get wedged in there. There's no other place for it to go. So now what I've done is now I've set my molecule up so that if I can now react this with steam, I can now strip off the SO3H group and basically unblock. So the SO3H, this is called the blocking strategy. I'm blocking that position so that the Br can only add ortho, and then I'm unblocking by taking off the SO3H group with steam. So we use this primarily when we want to put two groups ortho to each other, when a significant portion would go para. So we block the para position, and then we add the group ortho. So that's blocking and unblocking. Okay, so that's another dozen reactions to add to the benzene ring. Are we done? We're getting close. So let's now let's talk about the next sections in Top Hat are actually more of an introduction to what synthetic chemists really do. Most synthetic chemists most synthetic chemists that are working on making pharmaceuticals, they're not really doing the reactions that we learn this year. Some of them, yes, but a lot of them are using organometallic reagents, which means they're using transition metals that are more efficient, that I can use in water as a solvent. And so we don't necessarily touch upon that except this section, where I'll kind of give you an idea of what people may use. So we're going to have things like coupling reactions, where I'm going to take and add an alkyl group to a benzene ring using a transition metal catalyst. There are things like Suzuki coupling, there's Heck coupling. And so what do those kinds of reactions look like? And what I should do is I should start with, have we seen anything like this before? And that's a question I'm going to ask myself, because if I ask you, then you're going to have to turn your pages and try and remember back. And it was a long time ago. It was Grignard reactions, so that was like, what, a month ago? Which could have been like 3 years. So let's go back to what we talked about when we talked about coupling. And that was the idea of using what are called Gilman reagents or using lithium cuprates. So my goal here is to add any alkyl group I want to the benzene ring. And right now I'm kind of limited, right? I can add things with rearrangements, and I could add straight chained alkyl groups, but I've got to add the acid chloride, and then Clemenson or Wolff-Kishner reduce that. So if we think about back, what was the lithium cuprate? So from the lithium cuprate side of things, what we had was something with a lithium attached to it. So we had a lithium plus and a C minus. And we added to that copper iodide, copper 1 iodide. And I'm not going to worry about the stoichiometry here, but what we ended up doing was in this case, we've got 1, 2, 3, 4 carbons. So we ended up with 4 carbons with a negative charge, so butyl anion. We ended up with 2 of those, -1, and a lithium and a copper +1. So that was our lithium cuprate reagent. And what we did was we coupled that to any alkyl halide. So the alkyl halide that I think we should use now is I think we should couple that to a bromobenzene. Or couple it to a benzene ring with a bromine on it and whatever other groups I want. Because now if I'm going to couple that reaction together, I'm just going to get the 4-carbon, 1, 2, 3, 4-carbon group added to the benzene ring. Because those 2 alkyl groups are going to couple together using this lithium cuprate, or this is originally called the Gilman reagent. So if you think about this, using this methodology, because now we're like 3/4 of the way through the class, we've got a bunch of reactions under our belts, we can begin to think more universally about, well, most chemists are trying to make something, and they need to put these reactions together in order to make the molecule that they want. So in this case, if I think about using a Gilman reagent, where did the organolithium compound come from? It came from the alkyl bromide. And wherever the bromine is, that's where the lithium will end up. So look at all the flexibility, and I don't have that much flexibility, to be honest with you, but you don't know that yet, or won't probably know that. I do, because I studied these far too much. But wherever I put the bromine in my original molecule, that's where the lithium's going to go. And then that's what I'm going to end up adding, that carbon, that's the bond I'm going to form to the benzene ring. So I could, as long as I can make this alkyl group, or this alkyl halide, I can attach that directly to the ring, one stop. And that would include maybe having the bromine attached to the double bond, so that I could make the lithium compound out of that, and I could add the double bond directly to the ring. So this Gilman reagent it's something we've seen before, but now let's take a new look at it and say, okay, whatever my alkyl group with the bromine is, that's where the lithium's going to go. That's the lithium cuprate I'm going to make. And that carbon is what I'm going to add to my benzene ring. If I just use a bromobenzene. Jacob?
How would you add the double bond structure to the ring?
So what I would do is I do the same thing. I would add lithium metal to this. That would put, bless you, a negative charge here with the lithium plus. Change it over to a cuprate, and then couple it to the benzene ring. So if I followed the same exact methodology,
But wouldn't that not be enough to basically have the bond if ultimately?
it would end up like that.
Okay.
So it's this carbon that I'm going to end up adding to the benzene ring. So I would actually be able to make that in one method. So the idea is if I know what I want over here, just make that alkyl bromide over here. Okay. So that's the way these coupling reactions work. This one probably not the best because I'm still making like a Grignard reagent, which means it's going to be air sensitive, it's going to be moisture sensitive. But some of the other ones I could actually, if I change to a transition metal, I can do this reaction in water. That's going to make it green, a green reaction. I'm going to cut down on my waste. And those, even though those people haven't won Nobel Prizes yet, they all get names associated with these reactions. Things like Heck and Suzuki, Gatterman Koch. We'll talk about those reactions. And I'm just going to live lecture on that because I think the video I have online is kind of messed up. You could still find it in my YouTube channel, but I'm going to live lecture on that on Friday. So we're going to talk about these reactions. So if you have any questions, ask, email, come and see me. Otherwise, I'll see you on Friday, and that's your problems will be due then.
Question. Oh, I'm not home. Should there?
Let me